All right, so for this exercise, we're going to be using, there's a file under topology optimization. This is the video I'll be updating just because the old one is changed enough. So I'm going to hit download here. What you're going to do is at some point you're going to upload a screenshot. I'll tell you when we get to that point. And that's what you're just going to submit. Just so your results may vary from what I get, just to show that you worked through the exercise. And at some points I'll pause as we go through it just to answer questions around the room in case people get stuck. All right, so I got the file downloaded. It's going to be in my downloads folder. We showed a few ways to insert files into your schematic view. One way is you can drag and drop. So if I just download that, so this is my downloads folder, right? So if I right click and go to File Explorer, so right click to Start menu, File Explorer, and if I go to Downloads, or I can get there from my browser. If I go to the Downloads there and go to Folder, that'll take me to the same place. And what I can do is take that stuff file and just click and drag and drop right on my schematic, and that will load the file. It'll create a geometry block for me. Now I need to, so I just drag and drop my plate onto my schematic from the downloads folder. Now that doesn't have an analysis attached to it, right? So I still need to tell it, we're going to start with a static structural. So we take the static structural, and what I'm going to do is I'm going to click and drag and drop that on the geometry. So that's going to attach those two blocks. This is starting to show us how in the schematic we can start attaching things together to build up more complex analysis. So I'm going to take the static structural and drag and drop that on geometry. Okay, and the things highlight where you can drop it. The thing you don't want to do is drop it in one of these open spots. You want to drop it right on the geometry. So I'm clicking and dragging structural, drop it on the geometry. Now, as long as you have this connection from geometry to geometry, you're good. But let's say you didn't, so I'll show you what to do there. So I'm going to, don't delete yours, but I'm going to delete mine. So if let's say I just double click the static structural, right? It's going to put an open spot. I can still attach those, so I click and drag the geometry and drop that on geometry there, and that will create that connection. Okay, so this is what allows us to have one geometry that might feed into multiple different analyses. And so you should start building up, especially when you're doing optimizations, it helps them all to build up a set of analyses related to the same geometry. Okay, so now that we have this static structural, we need to add the topology optimization. This is one of the things that's changed. This used to be called topology optimization, but they've changed the name to structural optimization. So what we're going to do is we're going to click and drag the structural optimization and drop it on the results of the static structural. So structural optimization, I guess it has to be solution. You're going to drop it on solution to the static structural. You'll know you have it right if the engineering data, geometry, and model are all attached, and the solution is going to set up. Now, if it's not all attached, what you do, if it's all attached, you're good. If it's not all attached, just make sure you click and drag the structural optimization and drop it on solution. That's what wires everything up. All right, so now that we got that set up, what we're going to do is just double click on setup, and then that's going to, we see in the lower right, the lower left, the red shows that it's launching the mechanical window. All right, so this is, our mechanical window has opened. And again, we have to click on the geometry tab. Now sometimes we can't see our geometry. Let's see, the zoom, Z is zoom to fit, but that's not working. So I go to my geometry over here on the left, click the plate, and that'll show the plate for me. So that's the geometry I've inputted. I see, if I expand this on the left a little bit, I see my static structural. I see my structural optimization, okay? But there's some question marks I got to set up. And the way this topology optimization works is you set up the loads you're trying to optimize around. So we just load it like it's a normal part. Now the important thing with topology optimization is that it can only remove material. Okay, so it's going to set the density of material to near 0 if it's not needed. and it's going to keep the material that's still needed to bear the loads. So because of the way that works, you have to create your geometry so that it starts with as much available area as possible, and then it's going to remove material. Okay, so we're starting this whole plate. What we're going to do is we're going to apply a load here, vertical load, and then a fixed on the back here. Oops. Z, zoom the fit. All right, so in order to get my correct context menu, so I'm in static structural, I'll click that. Go to my environment context menu so I get the right options. I want to do fixed. I want to make sure I grabbed. Now I'm grabbing the face opposite of this load point. So I have a load point. I made a split line here. So I need to grab the face opposite of that. Hit apply. So that's our fixed boundary condition. Basically, we're making a cantilever beam that we're going to optimize. I need to do a force. And so I'll click that small patch. And again, like we've done many times before, we don't want a vector, we want it in terms of, in this case, it's going to be negative y. So switch from vector to component like we've done before. I forgot to apply my selection, so I click geometry, hit apply. And then in the y, we do minus 500. Okay, so that gives me minus 500 newtons. All right, so now if I click on my static structural, I see that I have my fixed constraint and my negative 500. So that sets up my static structural. But really what we're trying to do here is do the topology optimization. So I got to do, by default, it's all set up to do the topology. But just look at what's happening. So if I go, and we'll do the first run with just the default settings and see what happens. So we have the analysis settings. That's just more how the number of iterations of things that the defaults will work pretty well there. The main things we want to look at are the optimization region. By default, it's going to take everything except for where you applied boundary conditions. It's going to assume that where I put this force and where I have a fixed boundary condition, that's interfacing with other parts in the assembly, so you can't remove that. Everything in blue can be removed. Okay. And so sometimes you'll want to tweak that if you don't want it to be the whole domain. Then we look at the objective. The objective is what it's trying to minimize or maximize. Okay, so in this case, the default is to maximize compliance. Okay, compliance is stiffness of the structure. Sorry, it's trying to minimize compliance. Sorry, compliance is like the inverse of stiffness, so it's trying to maximize stiffness. Now, to maximize stiffness, you just keep all the volume, right? So I need to give it some constraint so it actually removes stuff. So that's where the response constraint comes in. And here, by default, it's set to reduce mass by 50%. Okay, so it's going to reduce mass by 50%, but it's going to choose the 50% that minimizes compliance or maximizes stiffness. Okay, so it's going to give us the stiffest structure it can while removing 50% of the mass. All right, so I have that set up. I'm going to hit solve. As this topology optimization is solving, you can expand the solution information and click topology density tracker. So these analyses can take a while, but this density tracker under solution information can show you the progress as you go. All right, so here, most of you got something that looks kind of like this. Now, obviously, this is not a great solution, right, because it removed too much material, but we can make some adjustments. So if we go to topology density, that's kind of the default result you get. What it's doing here is showing you the elements that have a density greater than 0.5. So everything varies between 0 and 1. So I can adjust the threshold here. So if I, again, click on topology density, retain threshold, I can drag that down a little bit. Now it'll give me a little bit better of a geometry. And then it'll refresh here. There we go. But we'd like probably something a little better than this. So there are some adjustments we can make. A couple things about topology optimization. It's very sensitive to mesh size. So it's really limited. It can remove or add material just at an element level. So if we reduce the mesh size, we give it a little more freedom. So let's do that. So we're going to go to our mesh here. So click on your mesh towards the top of the tree on the left. we're going to change the size from default, and we want to change the element size to 3 millimeters. So it's in meters right now, so 0.003, you get 3 millimeters. Double check the units there, so 3 times 10 to the minus 3, or 0.003, it gives us 3 millimeter mesh size. So I've played with this a little bit to get good results. So sometimes you have to play with it. So I'm just going to give you the numbers that kind of give a nice result, but keep in mind there'll be some iteration to do that. So what I'm going to do is, I know for this one, for the constraint, I'm going to do mass at 40%. Okay. Now, there's some constraints you can add to your problem that represent manufacturing constraints, okay? One thing with this reduced mesh size, there'll be multiple layers of elements through the thickness, and I want all the holes to be through holes. So I want kind of an extruded geometry so that everything's kind of just 2D. In order to do that, I need to add a manufacturing constraint. So I'm clicked on my structural optimization, and on the menu, I'm going to click manufacturing constraint and do extrusion. Okay. So what that does is make sure that my geometry can be an extruded shape. So in this case, I want it to be everything to be extruded in the Z direction, so that any holes go all the way through the Z direction, not partially through, with this thinner mesh, because there'll be 2 layers of elements. And so I do need to specify the direction for that extrusion constraint. And so the axis is defaulted to X. I'm going to switch that to Z. Okay, so again, I want structural optimization, manufacturing constraint extrusion. I'm not going to add it a second time. And then when I click on that constraint, I want it to be Z-axis instead of X. With those 3 changes, we change mesh size to 3 millimeters up on top. We changed response constraint to 40% instead of 50%, and we added manufacturing constraint. So now I'm going to click on static structural and hit solve again to redo that. All right, so what I'm going to have you do is submit a screenshot of whatever you got at this point. So click on your topology density. I'm going to go back to 50% here, 0.5. So I just want you to submit whatever it looks like at this point. So some of you have it, it's not running at all. That's fine. Just give a screenshot of your Ansys. Some people have a different shape, some drastically different. That's okay. Just take a screenshot of this, and this is what you'll submit for today's activity that showed you did it. The next step in all this, we have some geometry here that we've minimized compliance, but we don't know what the stresses are, right? So we want to do a check on this, run it to see if it's going to survive from a stress point of view. So in order to do that, we need to do a verification run, okay? So Ansys is set up pretty nicely to be able to do that. We can kind of convert this into geometry and then rerun it. So if I go back to the schematic view, all right, so we have to do this run a schematic view. And if I right-click results, it gives me 2 options. And this is only after I've run. Actually, one thing that's important here is if I go back to this view, whatever I've set for my retained threshold is what it's going to use in this next step. Okay, so right now I have 0.5. It's going to export this geometry to verify. If I wanted to have this 0.4 or a different value, I'd need to change that right now before I do this export. But I want it at 0.5. Okay. So once I have that retained threshold where I want it to be, I right-click results, and then I do transfer to design validation system. So it has 2 options, geometry and model. Geometry is what I want. That's going to allow me to bring it into what's called space claim. So I can do some modifications to it. So right-click your results on your static structural optimization. Click transfer to design validation system. That's going to create a new analysis block where I can run a simulation on the geometry I just created with the topology optimization. That's going to take a little bit to appear, okay? And so what it does is it connects the results into the geometry of that block. Right now I can't do anything with that block. It has this little green refresh. So what I need to do after that appears is right click it and say update. Why it didn't do that while it was doing whatever it was doing is a good question, but I think it's related to that retain threshold. If we change that, then we'd have to right click it and say update. So there's this connection, and it doesn't want to do that automatically. So right click and say the update. Now it'll take a little bit. So what that's actually doing is pulling in that geometry and bringing it into that block. So what we're going to use next is a tool. Ansys has its own kind of CAD-like tool called Space Claim, and we're going to use that to kind of work with the geometry. You'll find that Space Claim is really set up well to pre-process geometry to run into finite element analysis or to make changes, tweaks, scale things. In this case, we'll be kind of working with this geometry we got from cleaning up the geometry we got from the topology optimization. So it takes a little bit for this to pull it in. Okay, so after we did the right-click update, it's now ready. The geometry icon changed. So now if I double-click on geometry, it's going to open up Space Claim. And again, just like opening mechanical, this is going to be a completely different window now, but it shows the red on the lower left. That's how we know it's doing something there. And again, like opening the mechanical window, this does take a little bit. All right, so this is what we see in Space Claim. Now, one issue, there's a bug here. The scaling is going to be off on this part for whatever reason. So I'm going to verify that that's the case. I'm going to use the Measure tool. So go to Measure tab, hit Measure, and it's the same zoom controls as in Ansys. I'm going to click one node. It's measuring distance between nodes, and then control click the second. To get the second, I have to do control click. Once I have both those selected, it gives me a distance between those. Again, I'm on the Measure tab, click the Measure tool, click one node, control click the second node. So I see that it's 5,000. That should be 5 millimeters. I'm not sure why, because I didn't even change units in Ansys, so I'm not sure why it did that, but it always does it, even if you work in millimeters in Ansys. So we need to scale this back down again so we can work with it. Fortunately, that's pretty easy in Space Claim. So when we bring in a mesh like this, it's what Space Claim calls a facets model. So we go to facets, this triangle model. It has a scale option. So I'll click, so go to facets, go to scale. Now, whenever you enter a tool, it gives you a series of steps you need to do here. So the first thing, and it tells you what it's looking for. So the first click is click a facet body to scale. So that's this. I hover over, it turns yellow. If I click it, it's going to turn orange. Okay, so that gives me the body I'm going to scale. Again, I'm on facet, scale, and then I just click the body. I want to scale about the origin. I mean, it doesn't technically matter where I scale. Things will work a little better if I scale about the origin. So I kind of rotate my model. The origin is on the back. I'm just going to click the node that's at the origin as my anchor, as the point to scale about. So I'll click that. Then I'm going to zoom out with the wheel here. Now, it gives me this pull handle where I could scale it arbitrarily, but I want to scale it precisely 1 over 1,000, right? So in order to do that, I type 1 divided by 1,000. Okay, so you'll find this often in Space Claim where you can drag something to get kind of a arbitrary scaling, or you can type in a number to get it precise. So I'm just going to type in 1 divided by 1,000. It automatically does the math, and it's going to scale it down. Now, it does look like it disappeared. The reason for that is it's so small, right? So the zoom to fit button Z, hit the Z key, and that should zoom to fit. You know you got it right if it's now, we have that original plate that was there. We need to get rid of this plate. I don't want this plate here. So if I expand out this tree on the left, I see the plate shows up. I can unselect it. But it says it's still going to show up in the physics. Okay, so even though it's hidden, it's going to, what that means is it's going to show up in Ansys still. I don't want that plate in Ansys. So what I'm going to do is right-click the plate and say suppress for physics. And what that does is it's not going to show back up in Ansys. Okay, I just want this new geometry, not the old plate. So I right-click the plate on the left by expanding it, or sys1, right-click and say suppress for physics. So I'm left with this faceted body. So we need to convert that into a solid. Okay, right now it's a mesh. So in order to convert that to a solid, I'm going to escape out of the scaling tool. I'm still in the scaling tool. I need to go into design. So I need to extrude this as a solid. So I need to make a sketch first of the shape I'm going to extrude. So I go into design, I go into sketch. And now I'm just moving, I'm not hitting any buttons, I'm just moving the mouse around. And so that plane jumps around. What I want is to grab a point where the plane's parallel to the part, okay? And just click anywhere on that face, basically. So I get my sketch plane. So again, if I escape all this, I went to design, sketch. I'm just going to click somewhere in the front face of that part where that sketch plane is parallel to my part. It doesn't matter where the origin of that is. So you can see what it did is now all those facets that are on that plane become little lines, right? But those are not part of my sketch yet. I need to add those to my sketch. So that is pretty easy. What I have to do is left click and drag, draw a box around the entire thing. Okay, now I'm working within that sketch. So left click drag just to select everything. It becomes highlighted. Okay, then I do Control C, Control V. So Control copy, Control C. Okay, that copies everything I just selected. Control V, paste it. But the important thing there is now it's adding it to my sketch. It wasn't on my sketch before, now it's on my sketch. It's like in SolidWorks when you're doing extrusion, you need to have a sketch. So if I'm going to keep it there, but I'm going to Control Z just to show that again. So I'm on design, sketch, I pick somewhere on that face, then I draw a box around everything. Control C, or I could do, I'm sure it's up here somewhere. Control C, and then Control V to paste it. Now I have all that geometry on that sketch plane. The one issue I have here is because of the way my mesh was, some of these, it's not a very nice edges on this, right? So I want to clean that up. So the tool I'm going to use is the smoothing tool for the sketch, which will do a nice job of that. So what I'll do is, I think it's under repair, and I'm going to do fit curves. Okay, so repair, fit curves. I need to tell it what curves I want to smooth out, so I just, again, select everything. Okay, and I think it was selected anyway. So you can see what it's doing is it has, the green is what I started with, and the brown is what the smoothed out curves are. What works pretty well in this model, the maximum distance, I'm going to up that to 1 millimeter. And I'm going to switch to splines instead of arcs to give it a little more freedom in the shape of the curves. All right, and so that gives me the smoothed out geometry. Now I can play with that too. I could reduce that to 0.75 if I wanted to. Oops, I got to reselect everything because I clicked on the display. So it is adding a little extra material there. That'll be okay. Just leave it at 1. You could do arcs, try that, or splines. But I'll do lines and splines in 1 millimeter. So I'm going to click OK. And so what that does is it gives me that smoothed out geometry. I no longer need the faceted body, so I'm just going to unselect that to give me just the sketch. All right, so now the last step in all this is I do need to make this into a 3D shape by extruding it. So to do that, that operation is called a pull in Space Claim. So I go to Design, I hit Pull. Now there's a couple things I can do with pull. I can work on the 2D plane to add radiuses. So for example, if I don't want this to be a sharp corner, if I click the point, it's important to click the point with the pull tool. So again, this is design, pull. And I've hid the body just by unchecking it. So I don't see that anymore. But if I do the pull tool, click on a vertex, and then it gets this little arrow. If I drag that, I can add a radius to smooth it out even further. It's optional, but it's an additional tool you have to kind of smooth it out. And again, like the other tools in Space Claim, if I drag it, it's kind of arbitrary. I could type in a number to be more precise. Okay, so I have it kind of the way I want it. So the last thing I do with the pull tool is I can click an area instead of a vertex, right? So if I click the whole area of that part, I get an arrow that's perpendicular to that surface, and that's going to allow me to extrude it. Now I want to extrude towards my origin here, so I'm going to pull that extrusion to the right, in my case, but just towards the origin. It tactically doesn't matter. And so I pull it, and I get a number. But before I hit enter, I'm going to type in a number. So right now it's at 17, and I want this to be 5 millimeters. So I type in 5, and I hit enter. And so that gives me extruded volume at 5. Okay, so again, I'm going to Control Z just to show you that one last time. So don't worry about the rounding of the corners, but to get to this point, design, pull, click the area, drag that arrow towards the origin. Once that pops up, hit 5. And then enter. Okay. Now this P that comes up, later on we'll see how to parameterize things for optimization. We can, if we click that, it allows us to vary that from the schematic view. We'll see that later. All right. So I do have a split line here, which is important for where I add my force. If I did not have that split line, if your model does not have the split line somewhere in here, you do need to add that. The way you do that, you do split under design, and you click on the surface you want to split, and you just drag. It's approximately 10. This doesn't have to be precise, but if I want that at 10, what I can do is, I'm not clicking anything yet, and if I tab the mouse over to this, I can put in 10, and then I'll put a split line right at 10, but you can just click and put it anywhere. It doesn't have to be precise. But you just need one line there. If your model already had a line like mine, you don't need to add another one. But again, the split tool, click on the surface and just click somewhere to split it so that you basically can't have the whole top surface have the force. It has to be at the end. As long as you have some kind of split line there, it's fine. All right, so now it's done. So now it's a little weird in how space claim geometry goes into SOLIDWORKS. Sorry, Ansys. Normally you would save something at this point, right? And if you were working standalone in space claim, you would have to save. When I've launched it from Ansys, it's automatically saving in the background. So what I do is I actually just X out of this window, which seems completely bizarre, but that's what you do. Normally that would cause problems, but here it works. So you X out of that window, and now we're back to our schematic, and I want you to double click on setup. It says that upstream data needs to be read. That just means that space claim model we just updated, it's there, but it hasn't imported it yet. So then we'll have this long process of mechanical opening again. So after I close the space claim by hitting X, I just double click setup. And that's going to start the process of opening mechanical. Okay, so what we have here, if I go to geometry, we should, if everything worked right, I should have that geometry if I go to import geometry, hit Z, there it is. Okay. So the plate still came through, which it shouldn't have, so I'm going to right click the plate and do suppress. I must not have disabled the physics properly. So if the plate does show up, you have to right click and suppress it. So now I have the geometry. I do need to assign a material to it. So I got a bunch of question marks. What it does is it pulls the setup from the analysis I did before, but it adds question marks where it doesn't know where the geometry or what the materials are. So for this geometry, I need to set the material. So under geometry, click the second solid. In my case, there might be just one on yours. On the assignment, I click structural steel. And then so that gives me my materials. And I just go down and find the question marks, right? So fixed support, it shows me where it was, but it doesn't know what surface on this model. So then I just go to select that surface on this new model, click selection apply, and then same thing for the force. It shows me where it was, but it doesn't know where to put it on this model. So again, all I do is just left click the surface that's going to be the new force location, click apply. And then it's all ready to set up, so I hit solve here. So it's going to do an analysis on this structure, the actual optimized structure. Now I need to add some solution plots. So go to the context menu, results. Let's do total deformation. Let's do stress. Let's see, equivalent von Mises stress. Hit solve again to populate those plots. So this gives me the deformation of that model for that applied load, and also gives me the equivalent stress. I'll look at the max stress. So it gives me the results I didn't get from the topology optimization, right? So it allows me to check my, is it going to survive this 53 megapascals? It depends on the material I've chosen, things like that. So now I can do that verification.